Hi, my name is Peter Zeno, and I am presenting a kind of an introductory into a course that I give. It's a CUDA and GPU, actually CUDA C and GPU general purpose acceleration. So CUDA C is an NVIDIA specific programming language such that it is used on their GPUs, and it's used for general purpose. So GPUs are typically used and have been in the past just for 2D, 3D displays, but they went and made it so that you could use it in a general purpose, somewhat more easily programmable way, and I will go into that. So there's a bunch of links here. One is to my company website, and there you can sign up for classes. Most of them right now are one-on-one, and I do that over Google Meet. Excuse me, but this one I am working on putting it 100% on video. And so this, and so hopefully it'll be on Udemy, but we'll see. So what I will do is to put that into smaller segments, but still the same amount of time. So this course is typically a 5-hour course, and I will usually teach 1 hour at a time and then have the students work on some programming problems, and so I will address that as well, because I make it so that everybody can use Colab and Notebook and give examples in that. But if you have your own GPU and you want to do it on Ubuntu, or you want to do it on Windows, maybe through Visual Studio or whatever, then that is definitely up to you. But right now I'm making it so that everybody can do it and do it right through their browser, and be able to do that for free. At least it's free for now. And so this is a link to my LinkedIn, Xeno Robotics, and my GitHub, which has other links there for this class. It has other links to some documentation, online books, NVIDIA links, lots of information on CUDA. And then I am going to put this on my YouTube channel. So I typically have mostly just my autonomous robots on there, and videos of that and my drones, but I will start to include more of these. So today, hopefully in about 40-45 minutes, I will cover the evolution of NVIDIA's GPU architecture. So it has changed. It was just a fixed architecture up until the early 2000s, when they realized that something was needed such that multi-cores could be used in a general purpose way. And so I'll explain that later. And as well as the anatomy of a CUDA program, and GPU hardware. So the GPU hardware of this newly evolved since around 2006 has, besides having typical names for its graphical units, it has its general purpose, like streaming multiprocessors, streaming processors, and the way they're grouped, and they have an equivalent software vocabulary of what they're called. So you map one to the other. So you have blocks and threads and grids, and so I will cover that. And then I will then cover, somewhat mixed in the whole thing, I will keep addressing the memory hierarchy of the GPU, which is quite essential for for not only optimization concepts, but so you have to be very careful in your programming on access patterns, such as well, I'll go into that. I don't want to go into that right this second. So, so those are my robots, and those are the ones that are on YouTube, and they star in many of my videos. So I'm going to cover now the brief history of the evolution from just running your programs on CPUs to a heterogeneous CPU, GPU system. And it really depends on the program whether you can use it on a GPU or not. And so I will address what that's all about. So why CUDA? Why the CUDA architecture? So you may think, okay, CUDA is a language, but it's also an architecture. So the language maps to an architecture. Just the way that assembly language, which is low level, CUDA is not quite as low level as that, but it is specific, and it's best to know the hardware and how the hardware, the hierarchy of the memory, and you have to know like that you have a certain number of streaming processors and that they're grouped within a streaming multiprocessor, and what that means on what is that group of streaming processors can interact with memory or not. Can they talk to other streaming processors? So that grouping is very important. So the history is essentially that we had a huge growth, but following Moore's law, a doubling of transistors, so that was fantastic. Machines were able to do more because they were able to pack more logic because you have more transistors. Then clock speeds were increased, and they were almost essentially doubling every 2 years as well. But it got to a point where suddenly they were no longer able to get over 4 gigahertz because the number of transistors in a unit area were then doubled and doubling again. And so the amount of heat in that one area just would burn the chip if you were trying to run it at 4 gigahertz. So then it went back down to 2 gigahertz and then down to 1 point something. So that's why the clock frequencies were coming down, and it became an issue. So what they did was they went with multi-cores. So to make up for that speed loss, they would have 2 cores and then 4 cores, and so they're essentially doubling the number of cores. The problem, though, is that even though the hardware is able to scale that way, programs in themselves, not all programs are created equal. There is a lot of data dependency in some programs, more so than others. So if a program is such that there's a lot of, there's independence from one line to the next, because essentially your program counter is going to be doing the first line of execution and then the second and the third. So it's all sequential. But what happens is that a lot of times, say the thing whatever's happening on the second line is dependent on the change of the data on the first line. And when you start to put that through a pipeline, then there's issues with using old data and not new data. So as I was saying, like with NVIDIA's GPUs, they were just graphics accelerators for 2D, 3D graphics. And they're fixed function. And so this is an example of the hardware. So you would have these stages and essentially a pipeline, right? But the amount of time spent in each pipeline was not the same. So it may be doing some, besides your host interface, it may be doing some calculating of triangles, because everything becomes a set of triangles, and then creating meshes and working on shaders and all of that. It may spend more time in, say, one section as opposed to another, so there wasn't equal time. So it wasn't like a true pipeline other than being sequential. So Silicon Graphics released their Open GL, so their own programming language, but at the time that was not terribly straightforward to use and a little bit convoluted. It wasn't very good for general purpose. And so this just kind of addresses some issues. So in 2006, NVIDIA unveiled their GeForce 8800 GTX, which was the first GPU to be built with NVIDIA's CUDA architecture. So CPUs, they deal a lot with latency, and the latency is that of memory. So you're accessing memory, but I will get that. Anything big coming from main memory or whatever is off chip, and it takes time, and so you need to somehow hide that delay to keep things moving fast. And so if you look at say a CPU, so this portion would be on a single chip where you have your control and the ALUs. So you can see that the ALUs themselves only take up a smaller portion than the control logic, and then the amount of cache is quite large. And then you have the off chip DRAM. And the reason for the huge amount of transistors that is set aside for the control logic is for things such as a branch prediction. So that helps reduce if you do predict it right, and you don't end up having to flush out the pipeline. But you do take hits when that doesn't work out. So large caches to convert long latency memory accesses. So there's control to that too. There's a certain algorithm as to how long it's been there, when to kick it out of memory, when to bring new stuff in, and so that sort of information to try to optimize not going out into DRAM, and also dealing with hazards and using this data as well. You have to flag it as whether it's been modified or not, and such. So this is your typical 5-stage CPU. So I won't really go into it other than, this is almost like you would think this as a bank of registers. So to go from one register to the next and from one clock edge to the next clock edge, it has to make it through, say, getting data from the register file. First you're you're getting your instruction, fetching your instruction, and then you're decoding it, and then putting the right data through and performing whatever you're doing in your ALU plus or minus or whatever you're performing mathematically, and then writing data back. So that's your typical pipeline. And in such pipeline, so when there's branch instructions, which, like, say you have an if-else statement, and it is assumed it may just start out with a certain weight, say that in an if statement, the very first if is going to be taken 75% of the time. So it has a certain weight to it, and that may get, or typically will get modified over time, but that's a very simple example. There's certainly more complex ways of calculating and predicting that. But the problem is that you do have to dump the data if you're starting to execute along a line. So you start processing everything under that first if statement, but it ended up being false, and you have to go to the next statement, say an else statement, and that happens to be true. So then everything that had been flowing through gets flushed out. So that's part of the control logic has to deal with, and also that shows you latency issues that'll happen because of such a stall. And throughput is huge when it comes to GPUs, which is obvious if you know what's going on with the hardware, and I'll explain that. So, so if you look at, say, the equivalent of a GPU hardware, so this is, say, just a single chip, the majority of the chip is just computational units. So, and they are very much the same. Actually, they would be exactly the same, except there are some special function units sprinkled through, and tensor cores now are becoming a bit more abundant. But I'll touch upon that a little bit later. But as you can see, a very small amount of memory, so this is off-chip DRAM, this is devoted to registers and shared memory, typically. So this is mostly what you see here. So there's no branch prediction at all, because what you choose is code that is rather independent. You can unroll it if you need to do so. And it's so these are very lightweight calculations being brought through, but they can be done in parallel. So if they don't fall within some ideal parallel, say matrix multiplication, which a lot of things can be done in parallel and there's no dependency, then you want to go with the GPU. But say if it's a very small matrix, sending the data over and back and getting it back in the memory transfers, you would end up doing much better if you use the CPU. So this is just showing you, say, one chip versus the other chip, and just how much processing can be done here. And although you would call it general purpose programming, that it's really a specific type of data set. There has to be a lot of independence in this data set. So I kind of touched upon that. Parallel programming workflow, identify compute-intensive parts of an application. So you may typically run like a gprof on your program just to see what areas are, most of the time is spent in that program, and then you look at that time, and of course, to consider a speed up, you follow Amdahl's law, and so I don't think I have that in here, but that's something you typically find in your computer architecture class. So optimize data arrangements to maximize locality. So there's the sense of coalescing data when you access it in a GPU, such that you're not always thrashing. Well, one, you're taking a hit with DRAM because you have to do this refresh cycle every time you do a read, and if you're not doing a coalescing where it's a sequential amount of data that you can read in one batch, then you're actually taking up a lot of time to access that data and to refresh it as well. And so this is just this is your typical cycle. I mean, whether it's hardware design, system design, or anything else, you assess the system and whether you're parallelizing or whatever you're doing. But in CUDA best practices, they have this APOD where you assess, you parallelize, optimize, deploy, and then you assess again. And so you're always trying to tweak the system such that you're like, okay, so we've got this thing running about as fast as it can. It's optimized in its memory accesses and synchronized where it needs to be synchronized between the threads, and etc. So you can find the CUDA best practices guide. Just Google it and you'll find it on the video.Com site, and they have a lot of great stuff there. And so this is the history of pretty much cover all the way up to the Blackwell, which is the most recent that hasn't quite been released to the public, but people are, or companies anyway, are scoffing them up. But so you go by the microarchitecture, and so these are the older ones, so the first one is your Tesla, then the Fermi and the Kepler. So these are the names you typically would hear. And so you then know, okay, so you kind of know what the version of CUDA that's running and such. There's actually a lot of information you can get from it. But you can see that, of course, the fabrication process has continually changed, got smaller and smaller, hence more transistors per square unit area, and then so you go from 210 million 210 to 28.3 billion transistors in the Ampere. Turing is no slouch for sure, and then the most recent is the Hopper, so that's the H100 with 80 billion transistors and 144 streaming multiprocessors, which relates to 144 blocks, and we'll go over that in a minute. And so the Blackwell, which is really quite large and fast and has even more tensor cores. They started introducing tensor cores back in the Volta, and then they kept increasing in amount of that, and they really come into play when you're doing training of neural networks. And so that's one use case where they really shine in their linear algebra or matrix multiplication and things like that. But yeah, so if you want, you can find way more information under the wiki CUDA. So just do a search on that. They have some interesting things there. And yeah, so let me just go over the NVIDIA's GPU architecture. So the interesting thing is that no matter which microarchitecture you have in your system, you can write your code up to a point, I suppose, where your kernel that you're writing, the things to go in parallel, it's really not mapped perfectly, or it doesn't have to be. You don't have to think about the microarchitecture and how many streaming multiprocessors it might have, or streaming processors. Although if there's a huge difference from something really old to something really new, you may want to rewrite your program. But anyway, the compiler will, for the CUDA part, the CUDA NVCC, so that is the compiler, CUDA compiler, which has two parts to it, and I'll be covering that. It has your regular GCC or G++ for the C part, and so that whole thing that runs on the host computer, and this would be the device, which is the GPU. Actually, they both are, but I'll get to that in a second. So there's two parts, and so the part that runs on the device, that is actually a real-time compiler. So when the code gets sent over, it gets compiled and configured as to which hardware, what the hardware is, depending on the microarchitecture, and what the settings are for number of streaming multiprocessors and processors per streaming multiprocessor and all that. So, and that has to do with the indexing. So I'm kind of getting ahead of myself, but yeah, so I will get to that in a minute. But anyway, so in a device, which is your GPU, you have what's shown here as a multiprocessor. So you have N of them, but they're really typically called streaming multiprocessors, or SMs. And per streaming multiprocessor, you will have multiple streaming processors. So multiprocessor, which indicates multiprocessors, and then these are the processors within this block. And so the shared memory can be shared amongst all of the processors within a multiprocessor, but not between multiprocessors. So that's just another one of those caveats. And this one is pretty much what I was saying, how you do the mapping of, okay, this is a block. A block is a streaming multiprocessor, and you're going to have multiple blocks. And within a block, you're going to have threads, and each thread is actually, say, a line of code that is running on a streaming processor, and they're all run in parallel. So the number of threads being run at one time is typically the number of streaming processors, unless you don't need all of them. And then, so each thread has registers unique to it and local memory, but they all have access within a block to the shared memory. And then, so your host, which is your typical processor, running your operating system, and actually it's in control of the whole program. This is where you are doing your compile and your run. It converts within the program, it tells when to send the data, when to call the kernel, and all that. And I'll go over that in a minute. So here's kind of a better view of how things map. So this is the NVIDIA GPU. This is the Turing, so it's only a few families back. And this one has 14 streaming multiprocessors, or 14 blocks. And you can see that each one of these TPCs, which is a texture processing cluster. And the thing to keep in mind is that, yes, these are used not only as a massively parallel computer, but they're also used for your graphics. So they still have a lot of the graphics naming, such as vertex, input assembler, I think that's a raster, and so forth. And so you will see both naming conventions, but the only ones you have to deal with are the blocks, and so the grid, the blocks, and then the threads. And as you can see, within the same family, the TU-102 is quite mammoth, with 72 streaming multiprocessor or blocks and 64 CUDA cores. So this is yet another name for a streaming processor. So the CUDA cores are streaming processors. So you have 64 of them per streaming multiprocessor. So you end up with 4608 of these in total. So the CUDA program anatomy, let me just see how far we are into this. Okay, so the basics of really learning, it's twofold. So when you're looking at CUDA, you want to know, okay, what is this architecture? And how does this architecture map? And what are the rules? And it's not just the rules of what can access what, but how well you program. So you're not thrashing, and it's like handling something more than once when you can do all the handling of, say, data in your shared memory. And so you're not creating a lot of latency of pulling stuff out of DRAM, bringing it in, and putting it back out, and putting it in. If you don't have to do that, then don't do it, because you end up not getting a speed up at all. It may take, you can just totally mess up how well your performance is, whatever you can realize. So, so heterogeneous programming. You have memory separate DRAM memories, of course. The CPU is in charge. That is where you run the program. And so within the program running on the CPU, you will be calling to copy the memory of the data over to the GPU, and then you will tell it when to come back. And your allocation gets set up as well on the host computer. Okay, so the CUDA program pre and post kernel run, and so kernel is actually the program name of the portion of your CUDA program that's run on the GPU. So there's always the same steps you're going to be taking, no matter what your program is or how many times you may call a kernel. You may only call it once, you may have multiple kernels and call them at different times, but you're always having to manipulate the memory And rather than go through all that, I'll just explain quickly that, okay, so you have your host computer and you start allocating memory space, initializing it with whatever data you want to transfer over the PCI Express bus, and then you tell the data to transfer over with a special call, and so that gets sent to the external DRAM on the GPU. So this is your GPU, and then you load the program, the kernel portion, and the kernel portion will then pull, for each thread, it'll pull whatever data that is indicated within the thread and the ID or the index, and I'll get into that. And then at the end, you pull back the results so you can do something with it. So this is just, this is a vector addition, but I won't go into really the addition part, but just the memory hierarchy. So this is not the most exciting thing, but this is just something to be aware of, that this is in every one of the programs. So essentially you're setting up a bunch of pointers to, say, an integer or a float or whatever you have, and then you figure out what the size is. So you create this variable, or I guess you can not create it and just use this all the time. But anyway, so n would be the, say, number of threads, so it'd be the number of threads, but it would be also the number of elements. So this is a vector, so which is an array. So there's n elements in this array, and so the size of an int times n is how much memory you need. So then you can go and allocate the memory for the CUDA portion. That's going to be sent for CUDA, and also a host copy. And also you can, this one uses a random inits function. So it's just randomizing values for this A vector, randomizing for the B vector, and the C vector is the results that will come back. And so the CUDA mem copy is the one that's in control, that sends that data over, depending on what this keyword is here. So this says CUDA mem copy, but that will always be the same, but this part is host to device. That means it'll be sent from the host to the GPU. So it is sending first D sub A, which D was just put in to the prefix to indicate that it was a device, although you don't have to do that. So the array A is sent, and the B is sent, and then you call and launch the kernel. So you have these triple less than, triple greater than, which indicates that it is a kernel. But not only that, but in front you would have something that says global. So it's 2 underscores and global. Well, not when you're calling it, but when you're defining. I'm not sure if it was in here. No, so it wasn't included, but we'll cover that briefly. So when you call it, so this, the first number is the number of blocks that you're dedicating, and they're using only one block, or one streaming multiprocessor, and they're using n threads. And so this is just an example. That's not realistic, because that would be absurd, and the best way, or really the only way to get the most out of using a GPU is to use as much of the hardware, as much of the processors which makes sense, right? Because the more elements you have that are doing the same thing, say you have a group of ants working together, and let's say you have thousands of ants, but you only tell 10 ants to work on something out of the thousands of ants to move like pieces of dirt, okay? You don't want to do that. You want to get them all doing everything in parallel because it takes less time. And then once this is called on the host part, it just keeps going. It'll just keep going down, but when it comes to a CUDA memcopy, it will stop and wait. So it's going to wait until the kernel finishes, and then this device to host is when this will execute, and it'll bring back that memory. So that's this portion there. So there's computational trade-offs because the transfer over PCIe data bus, so you're transferring a lot of data over. It takes time to transfer that data. It also takes time to get it into one DRAM, then across the bus to another DRAM, and then from that DRAM into the processors, and then back and forth. So that's a lot of latency. So that's why you want to launch a lot of threads efficiently. And then when they're executing, you don't want them thrashing through memory as well. So you want to run a lot of threads in parallel. So this is just the mapping that I mentioned. So this is, say, the software part, and not only say, but it is. So you have a thread, and this is a CUDA core, which is a streaming processor. So each thread is executed by a core processor, and then you have a thread block, and that is executed by a streaming multiprocessor. So you have multiple processors all running in parallel. And so then you have your kernel grid, and hopefully that's the whole GPU that you're utilizing. So you have all these blocks, which are all the streaming multiprocessors, and all these threads. So this is that global that I was telling you about. So kernel looks like a serial program, and I will show you an example. We haven't really gone over an example, but it says nothing about parallelism other in its vagueness by an index, which is what you will typically see for an array or a matrix. So you write it as if it was one thread, usually. But actually will run on many threads. And so it's all based on this indexing. And the index is an index of, say, an array. So A sub I, A0, A1, A2, that index. And so these are a bunch of extensions that is added to C. And so you have host, which is default if it's on the host, or meant for the host. Global is what means that it's callable from the host and it's executed on the device. And device. So if it's called from the device, then you use device. And so if you have any kind of variables you declare within that kernel, then it will typically go by default into a register, and the scope of it is just for the thread, and it's there for the lifetime of the kernel. But yeah, so like I showed before, each thread has its own dedicated register or set of registers. And array variables are, if you don't declare it as anything else, then it defaults to local memory. So local is, there's quite a bit more latency to local, but that's where it resides, and then you have the scope for a thread, scope for the lifetime, of a thread for the lifetime of the kernel. But if you put shared in front of the variable, then it's definitely going to go into the shared memory. And if you say just device, then it will go into global memory, which is that off-chip memory. And so it's there for the whole application, but the thing is that global and constant memory is off-chip, and there's a lot of latency with that. And this is just kind of showing you, so latency within clocks, 400 to 600 for global, constant, texture memory. Shared memory is only for local memory. Like I was saying, is still a hit, 400 to 600, and registers 0 to 4. So 0 to 4 for registers is shared memory, so that's where your optimization comes in. So I'm not going to go into different types of programming models that are out there, nor the really low level if you want to look at the real assembly language, whether it's the virtual part or the actual for that hardware. But you can go to that level if you wish, and this kind of show you. So that's definitely assembly level. And so this is just a matrix multiplication problem. So you could see by looking at it, and if these matrices are very large, so when you have embedded for loops like this, that's an indication as to whether it's 1D or it's going to be two-dimensional. Threads that you allocate are three-dimensional threads, and so I won't really cover all of that, but that's something to look for. So really all you need to know for CUDA itself is to know C or C++, to some degree anyway. And you don't need to have any GPU experience, just learning the basics like I have taught, and just kind of experiencing it over and over again, writing programs just as you would if you were writing assembly level code for a microcontroller. So the other extension is the thread. So this thread ID, this block ID, and they end in X, but you would put a .x to get the X dimension, a Y for the Y dimension, and Z for the Z dimension if it has all three dimensions. Threads definitely do have three dimensions. The blocks, I believe you would only go with two. And block dim is a constant that is dependent on the architecture, so how many threads per block. And grid dim is also a constant, and it is the number of blocks in a GPU. Okay, so blocks of threads. So these are kind of like the worlds. One kernel is executed on the device or GPU at a time. Many threads execute each kernel. Each thread execute the same code. Single program, multiple data, single instruction, multiple thread. Threads are grouped into thread blocks. Kernel is a grid of thread blocks. Threads are scheduled as sets of warps. And so that's very important to know that in each warp, there's going to be 32 threads, and that an array that is, of course, larger than 32 is going to get split up, and you don't know how it may get split up. So one part of the array or vector may come before another that you would think logically wouldn't happen, but that's the way the compiler has scheduled it. So I will just kind of touch upon the indexing, and so that we don't end up going through a full class here. Just to give you a feel for the indexing, I won't go into the shared memory, syncing threads, and another set of slides I have on optimization, how DRAM works, coalescing, optimizations that way, and sets of programs and stuff to work on. I won't go through all those. Yeah, so this Hello World, I think I got rid of a bunch of slides because it was really kind of useless. Just showing you the anatomy of, say this is one CUDA program, you're going to have the kernel part, which you can't make out, but it says global. So this is what runs on the GPU. Then you have this serial, like the main, so that is the serial code, and the parallel code is just calling that kernel and getting the memory. And I showed you the flow in a program. So I'll just skip to the end of this. So this is going to show you an example to give you an idea of, first, let's assume you have n blocks or n streaming multiprocessors, but you're only going to use one thread in each block, which of course would not be worth it, but it is good for showing you how indexing comes about. So this example is using an add, and so this is the meat of it. So this is the whole program. So yes, there's nothing, if you look at the program, there's nothing parallel about it other than the index is going to vary based upon how it gets mapped by the compiler to a block. So assuming that you have 4 different blocks or n different blocks, this x will go from 0 to n minus 1. So c sub 0 is going to be equal to a, so the first element of this vector, and added to the first element of this vector goes into the result of the first element of that vector. And so essentially all of these additions get done at once, at least. Since we have multiple blocks and only one thread, so as long as it fits in with all blocks, if it's larger, then it would do as many it can in all of the blocks and then do it again in all of the blocks. Yeah, so this is what I was saying. So if you have, say, 4 blocks, this is what the index would work out to be. And this is just the memory allocation part. And so this one is to show you how the thread ID, the other one was the block ID, this is the thread ID. So let's say that we only have one block, but we have many threads. And so in the same way, each thread is going to have its own unique ID. And each thread is going to execute this line, this code. And so this is just doing the memory so this is just allocating the memory as you typically would, and this calls the kernel and then fetches data back and clean up. And so this is just a combination of using multiple blocks and multiple threads per block. So this shows you that, okay, well, it's going to have 8 threads per block, and you're going to have 4 blocks. And right now they're using this index m to be clever. No, not index, a constant. So m is the number of threads per block. But there's another way of getting that value rather than just setting a variable. So anyway, the index is calculated dependent on what the thread ID is. So you have all of these threads executing in parallel on one block, all of these executing in parallel. So let's say everything was able to fit in nicely and you don't have to warp things out. So these are all happening at the same time, say one computational time. So this would be your actual vector. And so the indices would typically in a vector start at 0 and go to the end. So this would have 32 elements. So what exactly would 21 be with respect to an index that you're kind of vaguely, kind of vaguely, but the compiler will figure it out. Well, it happens to be that it's the thread ID of 5 and the block ID of 2. And with this multiplier to be able to do its offset. So with 5 and 2, and then 2 times 8, so you have 1 times 8 will get you to this point, and then 2 times 8 will get you to this point, and then going over 5, the thread ID of 5. Does that make sense? So the thread ID of 5, okay, it's actually the 6th element, right? And the thread ID of 2, but it happens to be the 3rd block. But this M is actually, you can get it through the block dimension, which it's dependent on the hardware, and this one happens to have 8 threads per block. That's what the block dimension in the X direction is. All right, so that is about it for what I was going to show. There is also, I have a link to show you how to get things just to get started on Colab Notebook. So I will add that link at the bottom of this on the YouTube. So you can give that a try, give it a spin. There's actually an error in that example code, and if you can't figure it out, just get a hold of me, and I guess I should. Yeah, you could probably just comment there, or I'll try to put my email so that I don't get spammed in the link as well. So if you have enjoyed this, perhaps you want to purchase the class, do a one-on-one with me, and we can, if you have certain interests, I can kind of change what needs to be changed, added or subtracted, or just go over this. And the real thing is to get more experience in the programming. So my lip service of just taking all this in is really not going to stick unless you're writing different types of programs, trying to do different things, and you need a golden model. The golden model would be to do it first, do it at a small scale. You don't want to do something huge on a regular processor that is so huge that it either does a core dump or takes several days. Just to get the basic idea of whether you have a golden model somewhat, that it's working in your parallel code as opposed to how it's supposed to work when you're writing it in regular code. So it's always good to have a golden model, capture your results and compare the two so that you're sure. You can't always be sure. You can't always be positive until you really test it out. So this was actually 67 minutes or so that was a little bit longer, but I hope you enjoyed. And so, as always, please hit subscribe if you like this, and I will definitely put more up coming, whether it's going to be on basics of FPGA. That's another course that I offer. I also do some microcontrollers, robotics, anything robotics, drones, lots of different stuff, as you can see from my YouTube videos. So, so please like and subscribe. Thanks.